Hey, environmental students, I hope that you're all well. Um, I'm hoping that this is recording because and it did. Okay. Are we recording? Yes, we're recording. Okay, sorry, because I just did this entire lecture and it didn't record. I can't believe it. Oh my goodness. All right, so I'm starting all over again. That's okay. So, hey, how you doing? Today we're going to talk about ecosystems and how they function. Um, as far as my disclaimer for this particular lecture, just like before, there's some background noises you might hear because I'm in my house. I have a whole flock of parakeets that are chattering away. I have, you remember Aries the cockatiel. He's doing his thing. I've got the two dogs and I'm downstairs, so I have a parrot called an eclectus, a female eclectus, a big beautiful red parrot who loves to scream. She's kind of murmuring in the background like a cat, but she belts out a few good screams. So I'm sorry if you hear that as well. All right, so we'll go ahead and we'll get started. So we're talking about ecosystems today and this week. And then we also talk about toxins in ecosystems. This is an environmental class. And so that is where we go with this. For ecology with ecosystems, we talk about different types of ecosystems. For environmental classes, we talk about the human influences on ecosystems and what that means. So we'll talk a bit about biogeochemical cycling, disruptions in those biogeochemical cycles as far as nitrogen and carbon, different toxins in ecosystems, as well as what they are, biomagnification, bioaccumulation, what are endocrine disruptors? We address that. And then as far as what are the solutions as far as managing these toxins that are found in ecosystems. So ecosystems, what are they? You've probably heard of a few. Ponds are ecosystems, and forests and oceans and fields and meadows. But ecosystems are also, found under rocks. Ecosystems can be found in your dog's ear or under your fingernails. Basically, you just have a geographic area of any size, of any definition. And what you take into consideration is you take into consideration the living things and then the non-living components. So like a pond, for instance, it would be the fish and the frogs and the turtles and the algae, but then you're talking about the depth of the water and the temperature of the water itself, any pollution, dissolved oxygen, and then how they all interact with one another. And you have a very delicate balance in an ecosystem as far as all of these different parts, all of these different players, all of these different components and the things that live there, all depending upon one another and working with one another, that form a healthy ecosystem. Different parts of geographic areas that we will visit here. And these you probably remember from your 7th grade science class, right? The chunky stuff, your rocks and such. This is your lithosphere or your geosphere. All that air that surrounds us is our atmosphere. We have a hydrosphere, which is the water, and then the biosphere. And so basically, you have all throughout the geosphere and the atmosphere and the hydrosphere and then living things, you have components. You have chemicals, molecules that cycle all throughout these different components of any given ecosystem. Uh, we'll see the examples actually, but all living things are made up of these atoms, these molecules, carbon and nitrogen and oxygen and phosphorus, that whole periodic table of elements, everything is made up, all matter is made up of these different components, and many of these cycle into and out of different parts of, the lithosphere and the atmosphere and living things. So how does that work? We say that these are biogeochemical cycles. And bio meaning living, and geo meaning the earth, the rocky, rocks and such, and chemical, different chemicals. So like you have the good things, right? Carbon and nitrogen and phosphorus and oxygen. You've heard of the water cycle too. But there can be consequences if these biogeochemical cycles are disrupted with too much of what's already there, like too much nitrogen. What could happen? Too much carbon. What happens? Why is there too much carbon, and what are the consequences? But you also have then you have toxic stuff, whether it's a natural thing like mercury that usually just stays underground, but then enters a biogeochemical cycle. It's very toxic. Like, what's the consequences of that? And we have, in the last 70 years or so, we have all sorts of human-made, artificial, synthesized chemicals that are thrown into these biogeochemical cycles as well. And they cycle just like everything else. And what are the consequences to that? So that's where the major part of our discussion occurs. We start with the nitrogen cycle. We just have a few examples. Nitrogen is critical for for living organisms. It's found in our tissues as well as the tissues of living things. It makes up our proteins and our DNA and our RNA. And so, where is it found? And how does it cycle into and out of living things? Like, where do we get it from? Well, nitrogen makes up most of the air that we breathe. Oxygen's important, but most of it that we're breathing in is nitrogen, but we can't use the nitrogen that is in the air. We just can't breathe it in and say, hey, now I can build muscle because I'm breathing in that nitrogen that is essential to build a protein. Living things cannot use nitrogen as it sits in the air. So what has to happen is you have two ways. It's really, really cool. Lightning not only looks neat or frightening, but lightning actually breaks up the nitrogen in the atmosphere, because the nitrogen in the atmosphere is in the form of two nitrogens stuck together, N2, and it's too big of a molecule for us to use, and lightning actually breaks nitrogen apart. There you go. It has a actual function other than the whole physics end of it, and that falls to the ground as precipitation and goes into the soil. And actually, nitrogen in the atmosphere, as it interfaces with the soil as well, it's right there, but soil can't use nitrogen, even with lightning breaking it down. Plants that are growing in the soil can't use nitrogen even after lightning breaks it up. Also, at the interface of that atmospheric nitrogen to the ground, you have bacteria in the soil that do this, as well as some fungus. So the bacteria that's in the soil actually breaks nitrogen down even more to like an ammonia type of molecule that now plants can use. Plants bring in this nitrogen after it's broken down by bacteria, bring this nitrogen into up through their roots, and they use that nitrogen and they build that nitrogen into their own plant tissues. And now we then get nitrogen by eating those plants. That's the way we get our nitrogen. Now, something else we can do is we can eat the plants. We can not only eat the plants, have a salad or what have you, but we can eat the animals that eat the plants, because, the cow will eat the grass. We're not munching on grass that grows, but a cow will. and then uses that nitrogen from the plant into their tissues. And then if we have a steak, we're eating, you know, the nitrogen that it took from the plants and made into its own muscle tissue, and then we're eating that. So that's how we get our nitrogen. That's how living things, you know, the plants get it from the soil after bacteria break it down, and then animals get nitrogen by eating the plants or eating the animals that eat the plants. Now, how does it get back into the atmosphere? Is that, you know, when things die, when things decay, they that nitrogen that's in our tissues actually gets built back up again into N2 or N2O. There's an oxygen stuck there by that bacteria and that fungus again. It's so awesome. Like the bacteria in the soil convert the nitrogen from dead and decaying things back into atmospheric nitrogen, and it gets released back into the air. Now, as far as disruptions in this cycle, we've known for a really, really long time that, you know, yes, you need nitrogen in the soil for plants to grow, but there's not much nitrogen available in the soil. We say that is a limiting nutrient, that is nitrogen. And what we've known for a long time is that if you add nitrogen to the soil, that more plants will grow, or they'll grow better, they'll grow taller, they'll have a higher yield as far as, you know, fruit, you know, from an or whatever they're producing from an agricultural standpoint. Now we've known that for, you know, hundreds, thousands of years, that if you add some sort of fertilizer to the soil, that plants will grow better. And for a very long time, we didn't always know it was the actual nitrogen, but like if you add, you know, animal waste, or, you know, that whole thing where you add, you know, dead fish to the soil that was a old reference. That's what Native Americans knew as far as naturally fertilizing the soil for plants to grow better. But around like the 1940s, right after World War II, we had all these leftover chemicals, and we figured out how to make synthetic fertilizers out of those. Lots of nitrogen, and so we could take this and we can apply it over thousands of square miles of agricultural fields, all of these petrochemicals in massive amounts. And hey, you know, crops grew so much better, and you know, they're still applied, they still do. However, you know, we've added a whole lot more nitrogen to the party. And so all of this excess nitrogen in the biogeochemical cycles has consequences. So what happens is when you apply that much nitrogen, that much fertilizer, is that the excess amounts tend to wash away into a waterway. And all of that extra nitrogen in the water causes algae to get really super hyper excited and start to multiply, because algae needs nitrogen to grow, but then there's so much nitrogen that you wind up having these huge algal blooms. And it's these algal blooms when they just overtake a waterway, and then you have some die-off of the algae, which removes the dissolved oxygen from the soil. From the water. And then all of those plants, or all of those animals that depend upon dissolved oxygen in order to survive, can no longer do so. And like fish, for example, they have gills. They remove dissolved oxygen from the soil, and there is not enough for them to survive. And you have these large die-offs of fish. We call these events eutrophication events, or this is called eutrophication. And while it may be a nuisance to like a farmer's pond, it goes so far beyond that. You have these basic like dead zones in the Gulf of Mexico, where the Mississippi River, which runs right down the middle of the U.S., and drains off thousands of square miles of agricultural land. It's the breadbasket of the U.S. All this nitrogen gets dumped into the Gulf of Mexico, and right at the mouth of the Gulf of Mexico, you have thousands of square miles of dead zones. There's not enough oxygen in the water to support fish, and this disrupts ecosystems on a massive scale. But also, if we're looking at this from a anthropogenic, human-centered point of view, your whole commercial fishery in that area collapses. And this is a serious problem, not just the Gulf of Mexico, but all over the world. So this is something that, environmental scientists and biologists are looking for some sort of a solution as far as trying to curb the amount of nitrogen that we're putting into our soil. Also, acid rain. I mean, this is a big deal. You release a lot of nitrogen into the atmosphere through the burning of fossil fuels. And that nitrogen, as well as sulfurs, acidifies rain and causes problems with acid rain. It's a very serious issue. Carbon is another cycle that you may be familiar with as far as these biogeochemical cycling. How do humans get carbon? Well, in living things, it starts, it's hard, it's a cycle, so it's hard to, we'll start explaining by explaining the atmosphere. There's carbon dioxide in the atmosphere, and it's very important because it serves to keep our atmosphere warm. It traps heat, thermal radiation, which is important in maintaining kind of a steady temperature on our planet. During the process of photosynthesis, that is plants photosynthesizing, they take in atmospheric carbon dioxide through little tiny holes in their leaves called stomata, and they convert that carbon dioxide into glucose molecules through the process of photosynthesis. So they are able to fix carbon that way, because carbon is a major component of glucose. And then, animals then get their carbon by eating those plants, or eating the animal that eats the plants, just like obtaining nitrogen. You can have then the plants, or the animals that eat the plants, they respire. You breathe in, but then you breathe out, which releases carbon dioxide, which puts carbon dioxide back into the atmosphere. Plants do the same thing at night. They actually release carbon dioxide at night, kind of the opposite of photosynthesis. During photosynthesis, actually, oxygen is released in the atmosphere, which is awesome. During the decay of living organisms, that carbon is then released into the geosphere, released into the soil. Now, over millions of years, through heat and pressure, depending on how much heat and how much pressure, these fossilized remains of living things, the carbon that was in their tissue, gets converted to coal and oil and natural gas. It's in the burning of these fossil fuels that, especially as of late, that we've been releasing a lot more carbon dioxide into the atmosphere than biogeochemical cycling is used to. And it's the data shows that this excess amount of excess amount of carbon dioxide in the atmosphere has been causing disruptions in climate because of the warming effect overall, that as far as carbon dioxide's role in our atmosphere. We also notice that the ocean has more of an acidification occur because you have carbon dioxide, and water causes that water to be more acidic. And so we notice an acidification in our oceans as oceans uptake that excess carbon. Now, as far as ecosystems are concerned and biogeochemical cycling, we bring our discussion here to toxins that are in the environment. And there are lots of different classifications of toxins. Some of these toxins are human-made, they're synthetic. Others are natural, but are toxic to us. Just because it's natural doesn't mean that it's safe, right? So, yes, there's really, it was a politician, of course, who said something about, well, there's nothing wrong with that. It's found on the periodic table, for crying out loud. It's like, yeah, I wouldn't go licking arsenic anytime soon. That's on the periodic table too, but okay. Now they do fall into these categories, but we know that we have what are referred to as synergistic effects that are very poorly studied and that we don't really know much about. That as far as the combination of these chemicals that can cause problems, as we'll revisit that in a few minutes when we get to more of that concept. But it's really disheartening, and I use the word alarming a lot from here on out for this particular discussion. And that is, when we're talking about these toxic substances in ecosystems, whether they're human made or whether they're artificial, human made or natural, I'm sorry, is that, it's not something you can really avoid because they're pretty much found everywhere and they enter living things. And I'm going to just kind of talk about people for here for some of this. And they get into you in so many different ways. I mean, they say like we're swimming in this chemical sea, this chemical soup, and it's pretty much accurate because these substances can it's not just something that you would eat in order to get sick from or in order to have these deleterious effects, but it's also in the air that we breathe, the water that we drink, the air that we breathe. Think of when you think, well, the air looks clear and the air quality is really good today, but where these are mostly a problem are indoors, like in your own home. Like you get into a car and you have that new car smell. That's because of the chemicals that are in the materials that are used to make a new car, and it might kind of smell neat, but some of those are really toxic and they're getting into your bloodstream when you breathe them in. And even through the skin, some of us think our skin is a barrier between our insides and our outsides, but our skin is really porous and chemicals are leaking through the pores in your skin and into your bloodstream at all times, right? I mean, some of you may have had like medicines that are delivered that way and patches that you wear on your skin. They get absorbed slowly. But whether it's, like the lotions you put on your skin or the shampoos that you use or the soaps that you use, the residues from laundry detergent with the clothes that are against your skin, this is all getting absorbed into your bloodstream. And it's found everywhere. It's found in, we said it's found in water, it's found in food, it's found in air, and in air, it's found in the soil. I mean, I said these are, not it, but all of these are found there. And you see from the graphic on the left-hand side, through industry and manufacturing, it's not just like the effluence that's coming out of some sort of industry or manufacturing plant, like the waste, it gets spewed into the air or dumped into the water or chucked into the soil. But it's also, the products themselves, which have these toxic chemicals that you're bringing into your house or that are in your workplace or that are applied to agricultural fields that somehow that in so many ways are brought into your body. And you think, well, I live in a really remote area. I live far from any sort of industrial complex, or I don't live in a city, I should be fine. Well, the one thing is if you're if you live in the Lehigh Valley, you probably live pretty close to a cement plant, which that's putting all kinds of stuff into the air, um, depending upon where in the Lehigh Valley you live. But on a larger scale, like they are even finding these chemicals in the Antarctic and the Arctic just because many of these become airborne and then are carried by jet streams and then deposited in the most remote places on Earth. The Inuits in the Arctic are have these chemicals in their tissues, uh, even though they're thousands of miles away from any of this industry or any of these manufacturing areas. So we're not immune to that. These toxins can some of these have properties where they can bioaccumulate in the tissues of animals. If they're fat soluble, they can build up, and they build up in like through a food chain. And all that, when that happens, we refer to it as biomagnification. So, as something like, if you have, the graphic here shows mercury, you have mercury in the water and it's absorbed by the little guys, the krill. When you have something, whatever eats the krill, they take in the krill, and though that mercury then gets into their tissues, and then the tuna eats the salmon, and that mercury gets concentrated into their tissues and gets more concentrated as you move up the food chain. It's why they say you don't eat this type of fish, or you're limited. It's recommended you don't eat this type of fish more than like twice a month. It's because of, and those are the fish that are so high in the food chain, it's because of this concept of biomagnification. Now, there are those mentioned earlier that they're natural. Um, they're, you know, they're not synthetic chemicals that are very toxic to living things. Uh, Lead, mercury, arsenic. Now, that being said, uh, humans are responsible for releasing them into the environment where they usually are not found. I mean, most of these are found or tied up, or like they're tied up in rock, for instance, and it can sometimes be released like through volcanic activity, but through industrial processes, fossil fuel burning, we release them into the environment, and then of course they become problematic. As far as synthetic chemicals, now it's been so not I should say not that long that humans have figured out how to make these synthetic chemicals. We've become very clever. They have many different applications. World War II, again, was that was a big time for the invention of these particular chemicals. Technology at its best or worst, I guess, depending on how you look at it. And they are found all over, mostly, I should say, including in your home. There's lots of them, and you're walking around with over 300 of these in your body. And you think, well, I can avoid this, or like I won't allow my child to be exposed to them, my baby. But, as mentioned, they're pretty much everywhere. You can minimize your exposure by um, your consumer choices in some regards, choosing a different shampoo or natural products that you put on your skin or that you eat, or being careful of the water that you drink. But even newborns have these chemicals already in their system, pass through the umbilical cord. Um, this just keeps getting worse and worse. I'm sorry to deliver this terrible information, but and you see, as far as formaldehydes and PFCs, PBDEs, they're found in, your carpeting, your furniture, your electronics, soaps and detergents, glues and adhesives, air fresheners, vinyl tile. I mean, it's just basically everywhere. You see, here's a list of the most persistent. I'm not going to go through these one by one, but you know, they do have some practical applications as far as pesticides, insecticides, fungicides, which has helped humanity in many ways. But then, you know, we're talking about it's over and over again, carcinogen, 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 toxin, toxin, toxin. So it's pretty alarming stuff. Now, the most recent one that has come to light are the endocrine disruptors. And it's been found that some chemicals serve to mimic hormones, and they stimulate or inhibit the endocrine system from working properly. And you see all of these that are here listed on the chart and are found in common products that we've been exposed to for quite a long time, whether they're, you know, phthalates. Phthalates are what make plastics soft, and that's why you see the duck that's there, the rubber duck, or like children's toys have phthalates in them to make them soft. Phthalates also have a unique property in that they hold on to scent. It's, you know, one other thing that they do. So like any shampoo or soap that has a really strong smell, like springtime fresh or what have you, have phthalates in them so that to hold on to that smell. So the shampoo always smells good, the soap smell or the lotion, so they smell nice even after an hour or two after you apply them or that you use them. To different, you know, pesticides, flame retardants, which mimic hormones, and they've been documenting in humans lower sperm counts. They did an extensive study in Germany where their sperm counts are so much lower, and they attribute it directly to these endocrine disruptors. But they also note in waterways where they are, you know, literally swimming in these chemicals, these animals, where they have noticed that the male frogs producing eggs and male fish producing eggs. So it's quite alarming, the effect of these. And again, we're still learning about them. We're kind of all guinea pigs in this big experiment. You know, when you're talking about over 300 of these chemicals, and not just like individually, what do they do or what are their effects, but we talk about like the unknown synergistic effects. Like you talk about, you know, you've got chemical, you might know what chemical A does or chemical B or chemical C, you know, but what about the effect of A, B, and C, or 20 of these chemicals in certain environments? And we think about all of the things that ailments that are new, you know, relatively new to science, all of these, you know, different cancers that haven't been seen before, like food allergies that are so prevalent nowadays than when, like in the 70s, you know, when I was a kid, it was the occasional peanut allergies, but now we have so many. And I'm not saying this, but there are those who say, well, you know, what about, you know, autism? Why are we seeing so many problems with these types of challenges, you know, human health challenges? This is one of those, you know, some of the topics we cover when we talk about the challenges and then we talk about the solutions. It's like a really positive, like, yeah, there are the solutions, and this is what we found, and this is what we're working on, and here's how the problem was solved. And unfortunately, this ain't one of them, because where the solution lies is it's you know, science that collects the data. And as you'll see, there have been so few studies on these effects, but policy isn't made by scientists. They only make recommendations. They only do the risk assessment. You know, they can determine the toxicity, but it's, you know, the realms of politics and social considerations, economic considerations, and ethical considerations that where policy is finally made. And so we see extremely lax rules in our country and slow to act as far as the solutions to combating these particular problems, because, you know, there's so much of this that we don't know. And then, you know, you're talking about these particular chemicals are produced for sale, so for profit, and also are used in the manufacturing of something else that's being sold to the consumer, and that tends to drive the decisions rather than human health. Human health is a very small consideration in these particular decisions. And like, as you see, like the US versus a European model of this. Now, the European Union has a very strict approach, a very precautionary approach, where they'll do rigorous testing before releasing something onto the market. Whereas in the US, we tend to really not test a whole lot. Like, you see only 10% of chemicals have been tested for toxicity, and then 1% are regulated of those. A lot of times it's reliant on the industry to test themselves. They say, like, the putting the mouse in charge of the cheese sort of a thing. And for us, you know, we put things out on the market that have been have had very little of no testing. And then if we see there's a problem, that's when we do a recall. So we have a very much more lax approach than the Europeans do, as far as, you know, trying to keep some of these, or the ones that are deemed unsafe, out of, you know, our ecosystems. You know, we do have several agencies that regulate these sorts of things, as you see the list there. And we'll kind of revisit some of these as we go through the course, depending upon, like, for instance, the Clean Water Act we talk a bit about in water resources. But you know, it's still definitely a much more lax approach. Hold on, little Benny, I'm almost done. A much more lax approach than other parts of the world. Now, we have a more strict approach than some parts of the world. Like, there are some parts of the world that have very little environmental regulations with these toxic substances. So, you know, we're not the worst, but we certainly aren't the most cautious. We're not the best. Well, that's been kind of eye-opening. That's been a little hard to hear, but it is part of the course, you know, just understanding how ecosystems function, but, you know, the unfortunate parts of these toxins that are in ecosystems. All right, that's it for now. We'll hopefully see you all soon. Take care, guys. Bye.